What's up guys, and welcome to a brand new Python video. In this video we're going to be discussing abstraction through functions. And to do this I'm using the MIT OpenCourseWare lecture assignments, and this is number 4. So let's dive right into it with problem 1. So here's problem 1. We have to write a function called nestEggFixed, which is down here, which takes 4 arguments: a salary, a percentage of your salary to save in an investment account, an annual growth percentage for the investment account, and a number of years to work. This function should return a list whose values are the size of your retirement account at the end of each year, with the most recent year's value at the end of each list. So he's given us some equations. We have function of index 0 is equal to salary times save times 0.01. And then function 1 is the previous one, times 1 plus 0.01 times growth rate, and then plus salary times save times 0.01. So this isn't that hard to do, and over here he gives us all of our arguments. And down here he has provided a testing function. So you can see that we should be getting results close to these. All of this will be in the GitHub, so you can access it yourself. Alright, so let's get started. So the first thing we have to do is actually create the function 0, so the 0 term. So let's create this list called storage, and it's going to take the salary times save, and then multiply that by 0.01, because that is what we are starting with. After that, we can create our for loop, not our while loop. So for I in range 1 through years, since we have to go through our years, we can say new is equal to storage sub I minus 1, and then we can do the remaining of the equation, which is 1 plus 0.01 times growth rate, and then add our salary times the save times 0.01. Alright, and then all we have to do is append that to our storage. So storage.append new, and then at the end of the function we can return storage. And sorry for my indenting, which is not correct. It's 2 spaces, it should be 4. But just ignore that. And yeah, that's literally all there is to it. We're repeating until we finish, so from 1 through the amount of years we have, and then we're just using the equations he has provided. And now we can put these into, actually we don't need to do anything here. He has already put it into the testing function, we just call it. So test nestEggFixed. Let's run that. And look at what we get. We get 1000.0, which is exactly that. 2150, 2150, 3472.5, 4993.375, and then 6742, which is almost exactly, well, it is exactly, just we're missing a last digit, but yes, that is exactly the correct answer. Awesome. So that was just problem 1. It's that short and simple. Let's move on to problem 2. So here's problem 2. This first model is pretty simple. He's referring to problem 1 and what we created in problem 1. So clearly the market does not grow at a constant rate. So a better model would be to account for variations in growth percentage each year. So write a function called nestEggVariable, which takes 3 arguments: a salary, a percentage of your salary to save, and a list of annual growth percentages on investments, which is growth rates. The length of the last argument defines the number of years you plan to work. Keep that in mind. Growth rate sub 0 is the growth rate for the first year, growth rate sub 1 is the growth rate for the second year, and etc. Note that because the retirement fund's initial value is 0, growth rate sub 0 is in fact irrelevant. This function should return a list whose values are the size of your retirement account at the end of each year. So again, we have nestEggVariable provided below with all of its arguments and what they're used for. And then we have the testing function down here as well. So this function is in fact extremely similar to problem 1. So I would like to draw your attention to problem 1, which I have open right here. So I'm just going to copy and paste the code. Because we're reusing code, we're programmers, that's what we do. Alright, so now you immediately notice we don't have a variable called years and growth rate. So years, as he said very clearly, it's just the length of growth rates. So we can just replace that. And then instead of having a constant growth rate, we add an S and I because it's a list now. So we just have I over there. And that's literally it. There is nothing else to do. That's it. And now we can just test it out. So test nested variable, run that function, and let's see what we get. 1000, 2040, 3142, 4142, and 5266. And 26000. Yeah, whatever. So yeah, that's it. That was extremely simple and short, actually. Very concise. So yes, it teaches you a lesson. You can reuse code. It can really save time. But anyways, on to problem 3. Okay, so in problem 3, we have to write a function called post-retirement, which takes 3 arguments: an initial amount of money in your retirement fund, a list of annual growth percentages on investments while you're retired, and your annual expenses. Assume that the increase in the investment account savings is calculated before subtracting the annual expenditures, as shown in the table below, since we have our equations below. And yeah. Your function should return a list of fund sizes after each year of retirement, accounting for annual expenses and the growth of the retirement fund. Like problem 2, the length of the growth rates argument defines the number of years you plan to be retired. Okay, so here we are. We have all our equations, very similar to problem 1, that's why I have it up here. So again, we can just copy and paste. So take problem 2 and paste it. Whoops, this goes like that. Yep. So we can paste it in here, but the equations are slightly different. So I'm just going to copy this equation, replace this with that, and then down here it's the same thing. So do that, except savings can go there, so it's going to be that. And then it's not 0 since we're in a for loop, we have an I over there. And yes, that looks like everything. We got our expenses, we got everything in. Now we can go ahead and test this function. It's very simple. It's very simple, actually. Let's see if it works, though. Let's test post-retirement on that function. There you go. See 8,000, oh wait, no, that's 80,000. 54,000, 24,000, negative 4,800, negative about 35,000. Wow. And all of that was done. Alright, that was extremely simple. On to problem 4. So here's problem 4. Write a function called findMaxExpenses, which takes 5 arguments: a salary, a percentage of your salary to save, a list of annual growth percentages on investments while you're still working, a list of annual growth percentages on investments while you're retired, and a value for epsilon. As with problems 2 and 3, the lengths of the post-retire growth rates determine the number of years you plan to be working and retired, respectively. Use the idea of binary search to find a value for the amount of expenses you can withdraw each year from your retirement fund, such that at the end of your retirement, the absolute value of the amount remaining in your retirement fund is less than epsilon. Note that you can overdraw by a small amount. Start with a range of possible values for your annual expenses between 0 and your savings at the start of your retirement. Your function should print out the current estimate for the amount of expenses on each iteration through the binary search, and should return the estimate for the amount of expenses to withdraw. So, he's basically saying import problem 2 and 3 because we need to use their functions. And then there are 3 hints that I extracted from the paragraph. Hint 1 is start with a range of possible values for your annual expenses between 0 and your savings at the start of your retirement. This can be determined by utilizing your solution to problem 2. There you go. We have to import problem 2. Hint 2. Your binary search should make use of your solutions to problem 3. And luckily, we learned about binary search like 2 videos ago, I believe. So, if you didn't watch that video, you should check it out if you don't know what binary search is. And hint 3. The answer should lie between 0 and the initial value of the savings plus epsilon. Okay, so here we are. Here's the function. Here's our testing function. So yeah, let's just get started. Down here we need to import problem 2 and 3. So import problem 2 as P2 and import problem 3 as P3. Okay, and then we can start coding. So the first thing we need to do is determine our savings. So savings is going to be equal to, and we can use problem 2's function. So P2 dot nest egg variable, which takes salary, save, and pre-retire growth rates. And then, of course, this is going to return a list, so we'll take the very last value by doing sub -1. Okay, and then we need a low and a high, and I'll explain. And high is going to be equal to savings. So this is like kind of our range, so it gets closer and closer as we guess more and more. And now here comes the while loop. So while absolute value of high minus low, so this is taking the distance, is greater than epsilon, we can say expenses is going to be equal to low plus high divided by 2, averaging the 2 out. And of course, expenses is what we're going to be returning, because that is our answer. And then we have new savings, is what I'm going to call it. And this is going to use problem 3's function. So P3 dot post retirement, post retirement, yes. And this is going to take savings and post retire growth rates and expenses. And of course, this is also a list, so we're going to take the last value by doing sub -1. And now here comes the more binary search part. If new savings is less than 0, then we have to say high is equal to expenses, else low is going to be equal to expenses. Okay, and after that, we have to say expenses is equal to low plus high divided by 2. And now we can return expenses. So this is so we again average the 2 out and we come back in the loop. Okay, cool. Let's go ahead and run this function. Let's see what we get. Hold on. Oh wait, we didn't put in the test case. So test find max expenses. This is what I think problem 2 and problem 3 are printing out. Yeah. So just ignore that. We need the very last value. Here we are. 1229.95, and yeah, that's basically the same thing. Alright, great. One thing I did notice was probably take that out. Oh. Alright, so there you go. That's problem 4. And yes, we just solved our whole problem set. This one was a lot simpler, I would say, and easier to do. So yeah, like, subscribe, and I'll catch you in the next one.